And we know that heat transfer can be transferred in 3 ways. So we just heard in the song, the options are convection, the way that fluids transfer energy in currents, and we also have radiation through rays or waves, microwaves, or the sun's rays, or campfires radiating heat. And lastly, we have conduction. That happens when 2 solids touch and their heat is transferred, like when you fry your eggs on the stove or make pancakes. All right. So I'm super excited because today I am using my touchscreen monitor because when I'm using this, I can write on it, and you guys can see what I'm writing, and it's much easier to use than my computer. So, trying to figure out which way I need to go so that you guys are centered. There we go. That's better. Okay, so here we go. Damn, we already listened to that song. Okay, so today we're going to talk about insulating materials. First of all, why do we need insulating materials? So we've learned that a conductor allows heat to pass through it easily, and any metal is a good conductor. Insulator, yes.
I'm gonna have to log off because it keeps logging me out. I'm gonna try to figure out what's wrong, but I can get back on with you like during office hours or in a few minutes if I can figure out what's going on.
Okay, yeah, just hard reset your iPad and then try to come back.
Okay, bye.
All right, bye. Okay, and insulators are all of your non-metals usually. Insulators do not allow heat to pass through them easily. So, we have that heat is the transfer of energy by conduction, convection, or radiation. We've been talking about that for about the past week and a half. And often we want the energy to be transferred for heating. For example, when it's cold outside and you want to heat a room, you want the heat from the heater to radiate from the heater and then take the convection current and spread the heat around the room. So as it heats up on the heater, the heat will rise as it becomes less dense. And then as it moves away from the heat source, it's going to begin to get cooler, and it's going to condense and it's going to fall. And then that dense, cool air is going to move back towards the heater. It's going to heat up. It's going to spread out. It's going to expand. It's going to rise because it's now less dense. And as it moves away, it's going to condense again. And that cycle is going to continue until all of the air in the room is the same warm temperature. So that's when we want heat transfer to happen. That would be a good example when we want it to happen. However, there are going to be some times, especially when you are designing your animal shelter, you're going to want to keep your animal warm and not allow his or her body heat to escape to the cold outside in the winter. Or you don't want the hot air from outside coming into your cat or dog's animal shelter that you create. So we need to stop that transfer of heat, and that's what we're going to talk about today. Materials which are insulators can slow down or prevent energy transfer. So energy cannot be easily transferred during those things or through insulators. We're going to talk about the different materials that we might use in different situations, depending on whether or not we want the energy transfer to take place. And that'll be towards the end of the lesson. So first, we are going to look at the example of a solar water heater. And in the solar water heater, there are places in the solar water heater where we want the energy transfer to take place. So we're going to want to use a conductor there. But then once the heat has been transferred from the sun to the solar water panels for heat energy, once it's been radiated down and we capture that energy, then we're going to want to insulate it so that we can maintain the heat throughout the rest of the house. All right, so here we're going to watch a video, quick little short video, pretty much a GIF a GIF of how the solar water heater works. So here we go. So, oh, just kidding. Let's try this again. All right, so we're going to watch a short little video here. Let's try it now. There we go. All right, so the sun heats up the liquid inside of the collectors. And then the controller pumps the hot liquid to the water tank. So after it warms up, it pumps the hot liquid. The hot liquid heats up water inside of the tank. So the hot liquid goes down and warms up all the other water. And then once it heats up this water, the hot water is available for use throughout the rest of the house, like in your shower, in your washing machine, in the sink when you're washing dishes. Because we all know that dishes get clean better with warm water. All right. So where are the places that we want heat transfer to happen here in this example? Where do we want heat transfer to happen? All right, Elliot, I see your hand. Go ahead.
We want heat transfer to the sun. We want radiation to happen, like from the sun radiating down to the solar panels.
Yes, that's exactly right. So we definitely want heat transfer to happen from the radiation down to the solar panels. Excellent job. So once the sun radiates down to the solar panels, then what happens? Do we want heat transfer to continue to take place, or do we need a shift? What happens next? After we have the sun's radiation to the solar panels, we are encouraging that through conductors here on these solar panels, then what happens? Ocean, go ahead.
First of all, sorry about my cat. And second
Totally
of all,
okay.
that heat heats up the water, and the water pipe goes to the generator, or I forget what it calls, a solar water heater. It goes to the solar water heater, and it provides the hot water to the shower.
Okay.
Or anything that you would want hot water to.
Okay, so would we want a conductor or an insulator from this point of, when it exits the collectors to when it gets down to the hot water tank? Do we want a conductor or insulator there? What do you think? Ocean, do you have a guess there?
Sorry.
It's okay.
My hand was raised for the last time.
Okay. So what do you guys think? Let me check the chat. Okay, I'm not seeing any responses. What do you guys think from the time that it leaves the collector and it's now in the pipes running to the, what was that other thing called? Hold on. Let me see what the other piece is called. Okay, so once it gets from the collector down to the controller, down to the tank, what do we want there? Would we want insulators for the water to carry, or for the water to be carried down to the tank, or would we want a conductor there? What do you guys think? Anybody have any guesses? Okay, Kaylee says that we would want insulators. Kaylee, are you feeling daring? Would you like to explain why we would want insulators?
Yeah, I think we would want insulators for like the water tank thing, whatever it's called. I think we would want insulators for that, so not a lot or none of the heat will escape from the water tank.
Absolutely perfect. Kaylee is absolutely right. So we have two very, very different temperatures here. We've got cool water and we've got hot water. We do not want warm water. We want to keep the hot water hot and the cool water cool. So in order to keep those very different temperatures so that the house can be supplied with the hot water, we have to have it traveling in insulated pipes, because if they are traveling through conductors, then what's going to happen is the heat is going to transfer to the cooler water that's going back to be recharged. So we want to keep them the temperatures separate, and by doing that, we're either going to have a conductor wrapped in an insulator, or we're going to have just plain pipes made out of an insulator material. Because remember, conductors allow heat to pass easily. So instead of having blue and red here, all the water would be purple because they would all be at the same temperature. Does that make sense? Give me a thumbs up if that's making sense to you guys. So remember, insulators keep the heat in its place. So for example, let me see. Oh, there's my pen. I always lose my pen. All right. So for example, let's see. Where can I write it? We'll write right here. If I have two pipes, this pipe is made out of insulators, and this pipe is made out of a conductor. Now, normally, our water and our pipes are about the same temperature as the house outside, or inside, sorry. So we'll say the temperature of the water in these pipes is 72 degrees Fahrenheit. All right, and before long, winter is going to be here. And when winter gets here, the temperature drops. And it's going to be cold. So somebody give me a winter temperature. What might a winter temperature be? Somebody give me a temperature that we might see in the winter. Landon, give me a temperature we might see in the winter.
Like 42 degrees.
42 degrees. All right, that's pretty cold. All right, so it's 42 degrees Fahrenheit outside of our house. All right, so if we have pipes that are insulators versus pipes that are conductors, we're going to have very different responses here. First of all, is the water warmer or is the air outside warmer? Which of these is warmer? 42 or 72? Destiny, which of those is warmer? The 42 degrees or 72 degrees? Which one's warmer? And you can comment in the chat if you don't want to unmute your mic. It's up to you. But which is warmer, 42 or 72? All right, 72 degrees is definitely warmer. So we have identified 72 degrees as warmer than 42 degrees. Now, knowing what we know about heat transfer, which direction is the heat going to transfer? Is it going to transfer from the pipes to outside or from outside to the pipes? Alicia, can you tell me which direction it's going to transfer? Is the heat going to transfer from 72 to 42 or from 42 to 72?
42 to 72.
Okay, so 42 degrees is colder than 72 degrees. So you're telling me that heat transfers from cold to hot. Is that right?
I think so, yeah.
Okay. Thank you for answering. Naha, I see your hand up. What do you think?
I think it goes hot to cold.
Okay, so you think heat transfers from hot to cold. All right, so now we've got 1 and 1. Let's see. Who's going to break my tie here? How does heat transfer? Jamon, how does heat transfer? From cold to hot or hot to cold?
From cold to hot.
All right, from cold to hot. All right. So Trying to think. Thinking back to all the songs that I've listened to. I just want to make sure that heat transfers from the cold object to the hot object. So you're saying that the cold, whatever is cold, let me use blue here. Whatever is cold is going to give its cold energy to the hot object. So it's going to give all of its cold to the hot. Ella, what do you think about that?
Can you repeat the question?
I've got classmates who are saying that heat is transferred from the cold object to the hot object. So that means that whatever is cold is giving its cold energy to the warmer object. What do you think about that?
I think that the hot transfers to the cold.
Yes, I think you are correct. So, ladies and gentlemen, we have not been learning about cold energy. We've been learning about heat energy. So that means that whatever the hot object is, has more heat energy than the cold object. So the way that the energy is going to be transferred is from the hot object to the cold object until both objects are at the same temperature. We do not transfer heat from cold to hot. The only thing that causes the heat to change for one to get warmer and one to get cooler is that the hot object is giving away its energy to the cooler object because it has less energy, okay? So let's keep that in mind. So now we're going back up here to the pipes. We took a little detour. We're redirected back in the direction we were going. So now we have two sets of pipes. Both have 72-degree water flowing through them. So now we know that heat is transferred from hot to cold. So this heat is going to try to escape and warm up the 42-degree air around it. So knowing that, conductors allow heat to pass easily. So knowing that conductors allow heat to pass easily, it's going to be very easy for the heat to escape this pipe and try to warm up the air around it. It's pretty much going to be not helpful because there's a whole lot more air than there is in just one little pipe. So pretty much, basically what's going to happen is this heat is going to easily escape the pipe until the 72-degree water has lowered its temperature down to the same temperature as the air around it. Now, the thing that makes insulators different and important, because this is a circumstance where you don't want heat transfer to occur. So what's going to happen with the insulator is it's not going to allow heat to pass through it easily. So the heat from the water is going to travel up to the border of the pipe, and then it's going to be bounced back because heat does not transfer easily through the insulator. So maybe 1 out of 4 might transfer out, because I'm not saying heat cannot transfer through an insulator. It just does not transfer as easily. So most of the heat that tries to escape the pipe will be redirected back down into the pipe so that the water does not lose its temperature as quickly. Does that make sense? So insulators keep the heat in its place. So it keeps the heat in its place, so where it is supposed to be at. So let's go to our next slide and see what else we can figure out here. All right, so here is another diagram, and it shows a different solar water heater. Same concept, a little bit different design. And this shows how the cold water flows in the cold water intake. Right here. The cold water intake is right here. And down the long tubes, which are called the evacuated tubes. So it goes in the cold water intake and down the tubes and then back up around and back into the inner tank. The water warms up due to energy transfer from the sun. And then it flows to the storage tank at the top. So what I want for you guys to notice here is that we have energy transfer from the sun happening. We'll use a red sun. Okay. So the sun's rays are shining down and whoops, not going there. Sun's rays are warming up the tubes here. Okay. So when somebody wants hot water in the house, the hot water flows out of the hot water input and down into the house. Another thing that I want you guys to keep in mind here is that in this solar water tank, you have 2 layers. And this is very important. And this might be something you could use in your shelter. Because what happened is on the inner tank, that inner tank is made of metal, which is a conductor. But in order so that it helps to keep the water that's inside, that's heated up, it helps to keep it warm. But in order to keep the energy inside, it is wrapped in an insulative outer case. So the outer case is an insulator. So we have either styrofoam or plastic here wrapping a metal inner tank. So you've got double layers. Now my question from you is that when the cold water flows down the tubes, energy is transferred to the water from the sun. What type of heating is this? And we don't want to make the pipe out of an insulator because we want the water in the pipe to warm up. But we want to keep the heat in here. So that's why we wrap it in an insulator. Okay? But what type of heat transfer is it when the sun's rays shine down and warm the water that's in those pipes? Radiation, absolutely. So when the sun's rays shine down, we have radiation. Excellent job. Now, my next question for you all is, in the tubes part of the system here, we want energy transfer to take place. So specific materials are used to make energy transfer as efficient as possible. There is a shiny surface underneath the tubes called a reflector. How does the reflector help to increase the amount of energy that the water in the tubes receives? So here we have a reflector. Well, that didn't work correctly, okay? It's a shiny piece of metal, almost like a mirror, that is underneath the tubes. What do you think the purpose of this reflector is? Think about what reflector means. What is a reflection? What might the reflector do to help to increase the amount of energy that the water receives? And Elliot, I haven't heard from you much today. Go ahead.
What's the question again?
All right, well, if your hand is raised, I'm assuming that you know what I'm talking about. So Kaylee, you go ahead and try to answer the question. Okay?
I think that the reflector reflects the sun's rays back onto the pipe in case any rays miss the pipe, so it could heat up the water as much as possible.
All right, very good. So as the sun's rays are shining down on the pipes, sometimes some of the sun's rays are going to miss the pipes because the pipes can't absorb all of the rays at one time, all these electromagnetic waves coming back at them. So what the reflector is going to do is it's going to reflect the heat back on the pipes. So anything that missed the pipes the first time is going to bounce back and hit the pipes, hopefully the second time. So like this ray missed it, but then it's going to hit the reflector and it's going to bounce back and it's going to hit the pipes. Okay, so the reflector serves as literally a mirror for the radioactive waves. So a way that you might could implement this idea or this strategy in your animal shelter would be to like wrap something in aluminum foil and direct it towards your animal shelter. So then you're going to get radiation from the sun shining down on your house and radiation being reflected off of a mirror or aluminum foil or some other type of reflective metal back onto the house. So you're getting more than just one source of radiation. You're also getting the reflected radiation. Does this make sense? Yes, make it kind of like a greenhouse. It's a good idea. All right, are we making sense? What y'all tell me? I need to see some thumbs. Up, down, to the side. Little shaky. All right, perfect. See some nodding heads. Thank you to those of you who have your cameras on. Okay, all right. Here we go. So before we continue on, I have a timer set for 2 minutes. And I either want you to share with me privately in the chat, or you can raise your hand if you want to share your answer with the group. But I want for you to come up with your own definition for an insulator. Come up with your own definition for an insulator of heat. So your response is going to be like this. An insulator is, and you are going to fill in the blank. So your response should be like that, either privately to me in chat, or you can raise your hand and fill in the blank for the class. You have 2 minutes to think. Ready? Maybe. Go away. Go away. I don't know how to make this go away. There we go. Ah! Just kidding. Here we go. All right, 2 minutes. No, my timer stopped. We're just going to wait for the music to stop. All right. In order to get your full participation credit for today, you have to respond to this question. So I either need to see your hand raised or I need to see your response in the chat. right, it sounds like our time is up. So thank you so much to Destiny, Naha, Kaylee, Landon, Harlem, Ocean, and Ella who responded in the chat. And I've got a couple people with their hands raised. So Elliot, would you like to respond?
Yeah, an insulator is an item. It's a material that doesn't let heat go through it easily.
Okay. Excellent response. Alicia, what do you complete the sentence? An insulator is what?
Elliot took mine.
All right, well, tell me again. What is it?
An insulator is an object that doesn't allow the passage of heat go through the object.
Exactly. An insulator is something that does not allow heat to pass through the object. All right. So I have not heard from Sabrina or Sergio or Zariah. And some of those people are no longer here. So in order to be able to get full credit, you have to respond by the end of class. Now we're going to continue on for those of you who are following along and paying attention. So today we're going to talk about a few good insulators before I send you on your way to see how we keep our actual individual homes warm. So first of all, fabric is a good insulator because the woven fibers, sorry about that, I had a hard time getting that one out. The woven fibers of the fabric trap air between them. So here you can see the little holes in the fabric because this is zoomed in at a microscopic level, and you can see where there are holes for air to get trapped in the fabric. And we know that air is a poor conductor of heat, so that means it is an insulator. So the more we can get air bubbles or air pockets around whatever it is we're trying to keep warm, then the better off it's going to be, the harder it's going to be for heat to transfer. So fabric is an example. We also have, and a lot of times you guys, everybody here has on insulators right now on your clothes. Your insulator, your clothes, helps your body heat from escaping to the environment around you. That's why in the fall and winter, you start seeing people wear long sleeves and jackets. By the way, happy first day of fall. But that is because we use a fabric insulator to help keep our body heat with us. Now, we also have an example of styrofoam. So, your teachers love coffee. You might see styrofoam cups to help insulate their coffee, to keep it warm longer so we're not drinking cold coffee. We might also use paper cups or cardboard. I did not list those here because we've talked about those in the past. But styrofoam also has air pumped through it, through polystyrene. So styrofoam is very light and it's full of air pockets, which makes it a great insulator. Lastly, we have this thick plastic cooler. And a cooler is made of thick plastic. And remember, thick plastic is a much better insulator than thin plastic. So the thicker your plastic can be, the better it's going to be at retaining heat. Now, we usually use a cooler to keep items cool. What do we add to a cooler to keep the items inside of it cool? Harlem, thank you for raising your hand.
Sorry, that was for me to tell you something important. I had to go help my grandpa get something out of the car.
Okay, but you're back now?
Mm-hmm.
Okay, thank you. All right, what do we add in a cooler to keep the things that are inside of it cool? Ella?
We add ice.
Excellent. We add ice to keep the things inside of a cooler cool. Now, so that's like when you go to the beach on a hot summer day and you add ice to your cooler to keep your sandwiches cool or your drinks cool. Usually they stay cool until the ice melts because the ice slowly lowers or increases in temperature because you keep opening the cooler. So the heat keeps getting inside of the cooler and melting the ice. But for the most part, the ice helps to keep things cool on the inside. Now, could we add something to the cooler to keep whatever is inside of the cooler warm? We normally think of a cooler keeping things cool, but could we use a cooler in the same concept to keep things warm? So if we add ice to the cooler to keep the things inside of it cool, could we add something else to the cooler to keep the things inside of it warm? We don't use ice and we use something else. Okay, Ocean, you're good. Could we add something to a cooler to keep whatever is inside warm? Naha, do you think we could add something to a cooler to keep whatever's inside of it warm?
We could add like the instant hot packets, and you could sit them inside.
Oh, okay. So you're saying that if I put like hot packs, maybe the same thing as a ice pack. You put an ice pack in the freezer, it freezes, it stays cold. Well, hot packs are pretty much the same type of material, but you just put them in the microwave and they get hot. So you're saying I could put ice packs down in the, or not ice packs, hot packs down in the cooler to keep whatever's inside of the cooler warm. Kaylee, do you think that would work?
I do think that could work.
Okay. Landon, if it is 42 degrees outside in a wintry day and we put hot packs down inside of this cooler, do you think it will keep whatever's inside of it warm or will it get cold?
I think it would keep it warm because it's thicker plastic.
Okay, excellent. You think it would keep it warm because it's thicker plastic, and I'm going to elaborate on what maybe your brain is thinking. Thicker plastic is an insulator, so it's going to allow the heat to stay in and not escape. So, for example, the heat packs are going to be down in here, and the heat is going to go to the walls, and then it's going to bounce back because we have an insulator here, which is going to divert most of the heat back into the cooler. Occasionally, we will have a little random piece of heat escaping every now and again, but most of it is going to be reverted back into the inside of the cooler because of the insulator. Insulator makes heat transfer happen more slowly. So eventually, those heat packs would need to be recharged. Excellent job. All right, does this make sense? Is this making sense? How insulators kind of stop heat transfer or slow heat transfer? All right, thank you for those of you who are responding with a thumbs up or a head nod. I appreciate that. All right. So, your assignment today is in Echo. This is what your agenda looks like. You've already done number 1, so you can check that off your list. Then you're going to watch a short little video. I think it's about 5 minutes. And it talks about the science and what contractors use to help keep your house warm. What do they do to keep your house warm in the winter or in the fall? First day of fall. It is a little chilly outside. Well, I don't know if it is now. It was this morning when I came to work. And then you are going to complete the Pear Deck, keeping our homes warm. And then the Pear Deck is pretty cool because it talks about indigenous South American people and how they build their houses to help conserve the heat energy. So here's your instructions on how to access the Pear Deck. If you guys don't have any questions for me, you are free to go and ready to get started on your assignment.